Imagine traveling to the very center of our galaxy, 26,000 light years away, and finding a vantage point on the night sky. You'd see millions of stars, and on the horizon, a strange dark sphere rising. It's a black hole, an object so dense, nothing can escape its gravitational pull, not even light. This monster is 10 times the size of our sun, yet millions of times heavier. It's not the only one out there. In nearly every large galaxy, astronomers have found evidence of black holes, millions, even billions of times the mass of the sun. How did they form? And how did they get so large? Scientists are finding clues to the fate that awaits our galaxy and the universe at large. But how do you study something that by nature evades detection? Sometimes the universe lets us in on its most mysterious workings. An orbiting observatory called SWIFT. It had recorded a flash of gamma radiation, a kind of ultra-high energy light that is the signature of a cataclysmic event. SWIFT automatically relayed the information down to Earth. And within seconds, robotic telescopes in North and South America turn their gaze on the rising light. Astronomers dial into the data to see how bright and powerful the flash had become. Meanwhile, at giant observatories in Chile and in Texas, they zero in on it, using specialized instruments to split the light into all its different wavelengths. That tells them how far the light had traveled to reach Earth. What they find is that it had come from 7.5 billion light years away, halfway across the visible universe. Putting together evidence from ground and space telescopes, astronomers determined that the flash was a narrow but intense beam of light, and that most likely it broadcast the birth of a black hole. This singular moment is the endpoint of a violent chain of events in the core of a large star. All stars shine by burning light elements like hydrogen. In the largest ones, intense heat fuses these elements into heavier ones, like carbon, silicon, and finally iron. Like hot air in a balloon, heat and light from these nuclear fires creates an outward pressure that prevents the star's massive outer layers from collapsing inward.
Eventually that fuel runs out, the energy flows out through the star off into space. It can't go on forever. When the fuel runs out, the star starts to shrink.
And when that iron core builds up to about 1.4 times the mass of the sun, it can no longer hold itself up against the pressure, and it will collapse.
In some cases, as matter slams into the star's core, the impact creates a powerful shock wave that races back out and literally blows the star apart. Our galaxy is littered with the scattered remains of these supernovae, as shown in images like these from the Hubble Space Telescope. But what happens to the collapsed core of these dead stars? When a large star implodes, Its weight is enough to squash all the atoms in its core down to their nuclei. The result, an ultra-dense ember called a neutron star.
The density of a neutron star is something like taking a mountain and crushing it down to the size of a marble, about so big.
Neutrons can withstand incredible pressures. But if enough matter falls onto them, beyond a critical threshold, they can be crushed down to nothing. When that happens, a black hole is born. A black hole is gravity taken to the extreme. Its mass is literally packed into a point and enshrouded within a dark sphere called the event horizon. That sphere is the point of no return. Any gas, stars, or planets that fall in disappear forever.